Again, the component in row I, column J of the matrix product is the sum over the index K of products of the entries in row I of A and column J of the matrix B, where the inner index K is the same for the components in row I of A and column J of B. Again, K ranges from 1 to R in this case. The entries in row I, column K, and row K, column J of B. Again, the inner index is the same for the products, and so we call the product of a row of a matrix by a column of a second matrix an inner product. All right. So now we'll look at a special matrix or family of matrices. A matrix, all of whose entries are 0 is called a zero matrix. And is denoted by large symbol 0, or if it is important to emphasize the size, the symbol large 0 with the dimension or size m by n. So notice that there are many zero matrices, each having different possible sizes. So we come to our first theorem of this lecture. We're going to look at properties of zero matrices. And we'll see that the zero or that a zero matrix behaves as we would expect. The sum of any matrix A with the zero matrix of the same size is the same as the sum of the zero matrix and the matrix A, which is the matrix A. Second, the matrix A minus itself is the zero matrix. Third, a zero matrix minus the matrix A is the opposite of the matrix A, or is the scalar product of -1 with A. And fourth, the product of the zero matrix in A, that is, if we pre-multiply the matrix A by the zero matrix, this is the zero matrix, and we're assuming here that we have conformal size. And if we post-multiply a matrix A by the zero matrix, this is also the zero matrix. All right, so next we'll prove these statements. Okay, so the first statement, look at the components in row I, column J of the sum of the matrix A and the zero matrix. This is the same as the sum of the components now. As the components are numbers, it doesn't matter the order in which we perform the sum, they commute, so we have this is the same as the sum of the component in the zero matrix with the component in the matrix A, and this is the same as the component in row I, column J of the sum of the zero matrix and the matrix A. Now, every entry in the zero matrix is the number 0, and so this is the sum of the number 0 and the entry in row I, column J of matrix A, which is simply the entry in row I, column J of the matrix A. And so the sum of the matrix A and the zero matrix is the same as the sum of the zero matrix and the matrix A, which is the matrix A. All right? So second, look at the component in row I, column J of the difference of A in itself. And this is the same as the difference of the components. And so this is the number 0. And so A matrix, which has as all of its components the number 0, is the 0 matrix. And so we have that A minus A is the 0 matrix. All right, third statement. Look at the component in row I, column J of the difference of the 0 matrix and the matrix A. This is the difference of the components. Now, every component in the 0 matrix is the number 0, and so we have the number 0 minus the component in row I, column J of matrix A. So this is simply the opposite of the component in row I, column J of the matrix A, or we can also think of this as the scalar multiple of the component in row I, column J, that multiple being the scalar -1. And so we have that the 0 matrix minus the matrix A is the opposite of the matrix A, or the scalar multiple of the matrix A with the scalar -1. All right? So fourth statement, we'll look at the product when we pre-multiply the matrix A by the 0 matrix. The component in row I, column J is the sum over the index value k of the component in row I of the 0 matrix and column J of the matrix A. So this is the sum over index value k, where every value or every entry in the 0 matrix is the number 0 times the entry in the jth column of A. And so this is simply the sum of products, all of which are 0. And so this is the number 0. And again, A matrix that has as all its components the number 0 is the 0 matrix. And so we have that when we when we pre-multiply the matrix A by the 0 matrix, we get the 0 matrix. Okay, so fifth statement. We look at the component in row I, column J, when we post-multiply the matrix A by the 0 matrix. This is the sum over the index k of the components of the product of the components in row I of matrix A and column J of the 0 matrix. Again, this is a product where each of the elements in the 0 matrix is the number 0, and so this is a sum of products, all of which are 0, and so this is the number 0. A matrix that has as all its components the number 0 is the 0 matrix, and so we have that when we post-multiply the matrix A by the 0 matrix, we get the 0 matrix. So the 0 matrix behaves as we would expect, that is, like the number 0 in scalar multiplication. All right, so next we need to define a symbol known as the Kronecker delta. The Kronecker delta is given by the symbol delta, so ij, and is equal to the number 1 if the index values are the same, that is, if I equals j, and 0 if they are not the same. All right? A square matrix with 1s on the main diagonal that is entries in row I, column I. So 1s on the main diagonal and 0s elsewhere. Is the identity matrix, or an identity matrix, and is denoted by the symbol capital I, or if it is important to emphasize the size, I sub n for the nth order identity matrix. So, for example, the second order identity matrix is the 2 by 2 matrix that has 1 on the main diagonal and 0s elsewhere. And the third order identity matrix is the 3 by 3 matrix that has 1s on the main diagonal and 0s elsewhere. So notice that the component in row I, column j, of the identity matrix is the number 1 if I is equal to j, and is 0 if I is not equal to j. And so the component in row I, column j of the identity matrix is the same as the value of the Kronecker delta with those index values. All right? Next we'll look at a theorem. So let the matrix A be an m by n matrix. Then, if we pre-multiply the matrix A by the m order identity matrix, this leaves the matrix A unchanged. And if we post-multiply the matrix A by the nth order identity matrix, this leaves the matrix A unchanged. All right, so now we'll prove these statements. And we'll prove it component-wise. We'll look at components and show that components are equal. The component in row I, column j, of the product, when we pre-multiply the matrix A by the m order identity matrix, is the sum over the index k of the Kronecker delta with index values I, k, times the component in column j of matrix A. Now the Kronecker delta is 0 for any value where I is not equal to k, and so zeros do not change a sum. And so the only non-zero term is the one for which k is equal to I. And so this forces the value of k to take on the specific value of I, so that we no longer have a sum. We have a single product, and that is the product of the Kronecker delta with index values I. And again, the value k is forced to take the value I, so this is the component in row I, column j of matrix A. The value of the Kronecker delta with index values I is 1, and so this is simply the component in row I, column j of matrix A. And so when we pre-multiply the matrix A by an m-order identity matrix, it leaves the matrix A unchanged. All right, and so now the second statement. The component in row I, column j of the product when we post multiply the matrix A by the n order identity matrix is the sum over the nx value k of the product of the components in row I of matrix A times the component in column J of the identity matrix, which is identical to delta ij. Again, delta kj is only non-zero if k equals j, and so this forces the value of k to be j, and so we have the component in row I, column j of the matrix A times the Kronecker delta jj. Again, the value of Kronecker delta with these index values is 1, so this is simply the value or the component in row I, column j of matrix A. And so we have that when we post multiply the matrix A by the n order identity matrix, this is still the matrix A. It leaves the matrix A unchanged. All right. So there is an immediate corollary to this theorem. If the matrix A is itself a square matrix of order n, then whether we pre-multiply the matrix A by the matrix I, or if we post-multiply the matrix A by the matrix I, of course the identity matrix of order n, then this is the same as the matrix A. So the proof is trivial. It follows directly from the previous theorem with m equal n. Okay, so we have two notions now for multiplication where matrices are concerned. We'll let A be an m by n matrix. Then we have a scalar product, and we have a matrix product for the matrix A. The matrix A under scalar multiplication is unchanged when we multiply the matrix A by the scalar, the number 1, and this is the same whether we multiply on the left or right. And of course, the number 1 is equal to the number 1. Now, in matrix multiplication, we are multiplying the matrix A by another matrix, the identity matrix, and we still have the same matrix A. That is, A is unchanged if we pre-multiply by the m order identity matrix, and the matrix A is unchanged if we post-multiply the matrix A by the n order identity matrix. Now, in general, Im is not equal to In unless, of course, m is equal to n. So, in matrix multiplication, the element that acts like the number 1 is the identity matrix, or is an identity matrix. And whereas in scalar multiplication, there is a single element that acts, or a single element that is the number 1, for which it's true that whether we pre-multiply or post-multiply by that element, then it renders the matrix unchanged. In matrix multiplication, it depends on the size of the matrix A. If the matrix A is itself square, then the two elements are the same. But if the matrix A is not a square matrix, it's any general m by n order matrix or size matrix, then there is an element that renders the the matrix A unchanged, but there is a difference for that element whether we are pre-multiplying or post-multiplying, unless, again, the matrix A is a square matrix. But again, there is an element in matrix multiplication that acts just like the number 1 in a scalar product. All right? So now we'll look at a new definition. yet another operation we can perform on a matrix, which is called transposition. So let the matrix A be an M by N matrix. The transpose of the matrix A, which is denoted A superscript T, is the N by M order or size matrix. That results from interchanging the rows and columns of A. That is, the component in row I, column J, of the transpose of the matrix A is the component that is in row J, column I of the original matrix. All right?